All right, guys, welcome back. We're going to go ahead and start section 7.4, which is propositional logic and very simple logic. So, previous section we talked about what logic is. We talked about the need for having these sentences that get stored in a knowledge base, and we talked about what a model is. We talked about what a possible world is, and we talked about how there's going to be these variables and a combination of values assigned to those variables that are going to specify a possible world, right? A model that represents a possible world. So we're going to take a look at this in a little bit more detail now. I went through a very abstract example. It's probably hard to follow in the last video. So hopefully this will make things a bit clearer. First things first, we're going to have to come up with a syntax for this logic, for this propositional logic, okay? Now, the syntax defines valid sentences within a particular logic, and we're going to say that atomic sentences are going to be sentences that have a single propositional symbol. So a propositional symbol is going to be one of those variables, and those variables are going to represent in our model something in the real world. Now, the symbols themselves, they're going to represent some proposition that can be true or false, right? So it can be true that this thing exists in the world, or it is false that this thing exists in the world. So some examples of different propositional symbols: P, Q, R, W sub 1, 3, north, right? Now, there are two propositional symbols within propositional logic that have fixed meanings, meaning they just mean what they mean. Okay, they're not something that's going to be assigned a value. That is true, which is always true, and then there's false, which is always false, right? So in this system, in this logic, you have these variables that represent something, and they can be assigned true or false. We can construct very complex sentences, and this is going to be kind of familiar, right, from what you've seen in programming languages you've studied so far, the and, the or, the not logic, but there's going to be something new here also. Depending on the other math classes you've had, you might have seen this before already when you're doing proofs and stuff, but whatever. So complex sentences can be built from simpler ones. So what we do to build these more complicated sentences is we can use a combination of parentheses to override orders of operations, and we can use these logical connectives, right, which in C++ we referred to as logical operators, right? So there's 5 connectives in this logic, right? So we've got not, which kind of looks like this, I don't know what this looks like a 7, maybe kind of like a deformed 7 or something. So that's not, that's negation, that's logical negation. So not A is the negation of A. So that not just takes the truth value and flips it. So if A was assigned true, then not A would be false. Okay, and then you got your and, which looks like an upside down V. So A and B is the conjugation, or said to be the conjugation of A and B. So that's going to follow, rules that you're used to, right? So A and B, for the entire thing to evaluate the true, A has to be true and B has to be true. Otherwise, it's false. You got your or, which looks like a V. So that works similar to what you're used to, A or B. Either A or B have to be true in order for the entire thing to be true. The only way it's false is if both A and B are false. So this is known as a disjunction of A and B. We got implication, which is this arrow, right? So in the text it uses this kind of open bodied arrow here, but it's an arrow. So the sentence A and B implies not C, this right here, this is a complex sentence. You've got a bunch of connectives, right? And you're using your parentheses. So this right here, this is called an implication. A and B implies not C, right? So the premise is A and B, so this first part right here is referred to as the premise, and the not C part here, that's referred to as the conclusion, right? So if you took your philosophy class, a lot of this language is going to be very, very familiar. Okay, so you got if and only if, right? So that's kind of like this double-headed arrow. So this is known as a biconditional, right? If and only if. So what that means is that for A if and only if B to be considered true, both A implying B must be true and B implying A must be true. Okay, so it has to go in both directions. All right, so here's a BNF summation of the grammar, right? So, I'll just let you stare at that for a second. I won't go through it. I mean, you've had BNF in your earlier classes. Okay, so semantics, right? So, as we know, semantics means meaning. We talked about that last time. And the semantics in this logic are going to define the rules for how you figure out if a sentence is true in the context of some model, right? So, propositional logic, your model is just taking the truth value, true or false, and assigning it to every propositional symbol. So here is one example, right? So we have some model, M1, and this right here is a possible model, right? So this is, for some world, M1 is one of the models for that world. So you've got propositional symbol A, you got propositional symbol B, you got propositional symbol C, and so A was assigned false, B was assigned false, C was assigned true. Now remember, A, B, and C are representing something in a possible world, in a real world, and maybe in the environment that the agent is operating in, right? Or maybe the environment that you're operating in. So we haven't defined what A and B stand for, but in this particular model, in this particular possible world, whatever A represents is false, whatever B represents is false, whatever C represents is true. So in this case, with these three variables, that's going to lead us to 2 cubed equals 8 possible models. Okay, so this is one possible model. This is one possible world based off of how the truth values are assigned to those propositional symbols. All right, so sentences are built from atomic sentences and connectives, as we saw. So the question becomes, how do we compute the truth of those sentences? Okay, well, true is true, false is false. That never changes. Okay, now, the truth value has to be specified in the model itself. So false has to be assigned to A, false has to be assigned to B, true has to be assigned to C, etc. Let's go ahead and look at a couple of facts for complex sentences, how this breaks down, okay? So, not P. That's true if and only if P is false in some model M. That's what this means, right? So, if P is assigned to false, if P is assigned false, well, not false is true, okay, for that model. P and Q, I already kind of gave you a summary of this already, but it's true if and only if both P and Q are true in that model, right? So, just like what you're used to with logical operators, P and Q, right? If P is true, Q is true, the whole thing's true, otherwise it's false. P or Q, same kind of thing, right? If P and Q are both false, then the whole thing is false, otherwise it's going to be true in that model. P implies Q is true, unless P is true and Q is false. So this is always going to be true. The only time it's going to be false is if P is true and Q is false. The bidirectional P and Q here, that's going to be true if and only if P and Q are both true or both false in the model. An alternative way that we can present those facts, truth table, right? So here's a summary of all of those facts. If P and Q are false, not P is true, P and Q is false, P or Q is false, P implies Q is true, and the bidirectional is true. So we can find the truth for any sentence, okay, by using these rules for any model. Okay, so let's look at an example from that previous model. Remember, M1 had assigned A to be true, or excuse me, A to be false, B to be false, and C to be true, right? So remember, right, M1, in that model, in that possible world, A is false, B is false, and C is true, right? So all you do really is just plug and chug. You just do a little substitution here. So if A is false, then not A evaluates to true, right? Now B or C, if B is false, C is true, false or true is true. So then that whole thing evaluates to true and true, which gives you true. So this sentence is true within that model, okay? Now, P arrow Q, that can be read as P implies Q, or if P then Q. Again, we got some of this philosophy language going on, right? So in propositional logic, 5 is odd implies Tokyo is Japan's capital. That's true, right? It sounds kind of weird, but it's true. 5 is odd implies Tokyo is Japan's capital. That's true in propositional logic based off of the definition of how implication works. All right, so any implication is going to be true whenever its antecedent is false. So this is false right here. So long as that's false, according to the definition, the whole thing is going to be true. Because if you go up here and you look at P implies Q, right, when P is false, the whole thing evaluates to true. So it doesn't matter what Q is in that situation, right? So basically, you know, if you say what you're saying is, you know, I'm going to make some kind of claim, or I'm going to say something about a claim. If P is true, then I claim Q is true. Otherwise, no claim, right? Now that's only going to be false if P is true, but Q is false. So basically, let me see if I can give you an example here. You know, if my premise is garbage, then whatever I claim to follow from that premise, you can say it's true whatever you want, right? If I say unicorns exist, therefore climate change is a hoax. Okay, that implication is true because unicorns existing is false. Let's see here. I talked about the bidirectional. It's true whenever P implies Q and Q implies P. If and only if, that's that logic. So here's an example from Wumpus World. A square is breezy if an adjacent square has a pit. And a square is breezy only if an adjacent square has a pit. So how could we represent this in the propositional logic using symbols? Well, we have a square in 1, 1, right? The 1, 1 square. It's breezy. Okay, so it's breezy if and only if there is a pit in 1, 2, which would be 1 square above it, or there's a pit in 2, 1, which would be 1 square to the right. Okay, now you could say also that you know, going the other direction. If there's a pit in 1, 2 or 2, 1, then 1, 1 must be breezy, right? So it works in both ways. Let's look at a simple knowledge base, okay, and then I'll walk you through an example here. Okay, so all of the immutable aspects of Wumpus World, right, all the things that won't change, okay, so the position of a pit, okay, the position of the Wumpus, whether you smell something, you know, whether there's a breeze, those things are going to be assigned to a square. They're not moving. Okay, the agent's position can move, but these other things won't, right? So take a look at this first line, P of xy. That'll be true if there's a pit in xy. Say P22 is true if there's actually a pit in square 2, 2. WXY, that's true if there's a Wumpus in xy, whether it's dead or alive. BXY, that's true if there's an agent, or if the agent perceives a breeze in xy. Okay, so if there's a breeze in square 3, 1, then B of 3, 1 is true. Okay, and then similarly for smell, or for the stench. Okay, so let's take a look at an example that will hopefully tie some of these ideas together and, you know, peel back some of the abstraction and see how this is applied, right? So, example of Wumpus World, very beginning of the game, and remember, what were some sentences? Let's put together a simple knowledge base, right? And what were some of the sentences that we can add to that knowledge base, or what are some of them, right? Well, when the game first starts off, by rule, there is not going to be any pit, no pit in 1, 1, right? Because you die right away, right? You could also say that there cannot be a Wumpus in 1, 1, okay? Because the game would be over right away, okay? So we know that. Now let us also say that my agent does not perceive any stench, right? So no stench in 1, 1. Okay, so what does that imply? That implies that there's no Wumpus in 1, 2 or in 2, 1, right? Now let's also say another sentence where the agent does not perceive any breeze, right? So if the agent doesn't perceive any breeze, let's add that to our knowledge base. So there's no breeze in 1, 1. So in that particular world, all of these things are true. Okay, All of these things are true. There is no pit in 1-1. There is no Wumpus. There is no stench. There is no breeze. Okay, so from that, I can entail from my knowledge base that it's okay for me to move into either of these squares. So let's say that the agent flips a coin and decides to move to 1-2. At that point, the agent perceives through its sensors a stench. Okay, so we're going to add to our knowledge base the fact that we did perceive a stench in square 1-2. Okay, so we're learning as we're moving and we're sensing, we're perceiving, we're getting percepts, we're learning more about the environment, we're adding the information to our knowledge base. Okay, so now at this point, if I perceived a stench, then based on the rules, right? Remember we had a rule that said, based on how the game's played, that a stench implies you have a stench if and only if there's a Wumpus in an adjacent square, right? So there's going to be a Wumpus in either 1-3, there'll be a Wumpus in 2-2, or there'll be a Wumpus in in 1-1, according to how the game's played. Okay, so I'll write that in here, 1-3, or Wumpus will be in 2-2, or there'll be a Wumpus in 1-1. Okay, because if you see a stench, there must be a Wumpus nearby according to that rule. Okay, so now I want to see if my knowledge base, will that entail, let's say I want to determine if it's safe to move into square 1-3. Does my knowledge base entail that there is no Wumpus in 1-3, right? So that sentence right there would be my alpha, okay? So how am I going to figure that out? Well, I'm going to use a simple inference algorithm. And what that inference algorithm does is it has you create a truth table. Okay, I want to make that smaller, but I guess that's as small as I can make it. Yeah, that's as small as that's I wanted to make it small. That's as small as I can make it. Okay, anyway, so you're going to make a truth table. Okay, so what are the variables that I need to assign values to, right? Well, I've got my stench detected in 1-2, right? And then I want to know about the square for 3-1 if there's a Wumpus in there. And I say 3-1, but I meant 1-3, sorry. Okay, what about a Wumpus in 2-2? And what about a Wumpus in 1-1? Okay, so I'm going to be assigning different combinations of truth values to those variables, to those propositional symbols. Okay, now what is not Wumpus in 1-3, right? That's what I'm trying to figure out. Okay, and also I'm going to have to figure out this rule right here. This is going to have to hold along with my not W13 in order for me to be able to conclusively tell whether or not there is a Wumpus in that square or not. And so it'll have to hold for every possible world. Now each row within the truth table is going to represent one of the possible worlds, one of the possible configurations, right? Each one of these is going to be one of the models for the world. Okay, so we got that, and then we'll have to evaluate this, or W22, or W11. Okay, so these are my propositional symbols, okay, and these are sentences. Okay, this is a complex sentence, R6 is, and then this is atomic, right? And this has got a connective in it, right? So, well, I say connective, but the connectives are more like ors and ands. So this is definitely atomic. You could argue that these are atomic also, but they do have this extra piece here. So maybe not, right? So got that, and then R6, okay? So rather than write out this whole thing again, I'll just put R6 here, okay, to represent that. So you just go through and you start iterating, right? You start enumerating all the different possibilities. So what about a possible world where all of these things are false? Okay? What if a possible world where all these things are false? So if that's the case, then not W13 would be true, right? So what does that mean? Well, if W13 is false, that means no Wumpus is in there, which would mean that this is true. There is no Wumpus in W13, okay? Now, what about this right here? W13 or W22 or W11, that or, they're all false, so false. So that tells me, this statement right here is saying, is there a Wumpus in any of these squares? False. It is false that there are Wumpuses in any of these squares. Now what about the bidirectional? Now the bidirectional is only true if both of the sentences that are connected, if they're both true or if they're both false. Now, false, false, true. Okay, so that holds up. Now that's just one potential world. Okay, so if I look at this and evaluate it, you know, this says no stench, no adjacent squares having Wumpuses. Okay, now go through and you enumerate the next model, the next possible world. So let's see here. So the opposite of false is true. Okay, now, is there a Wumpus in one of those squares? Well, according to this, in this world, yeah, there is. Okay. Now, does this hold? Is false and true true? Right? No. For the bidirectional, no, it's false, right? Because they both have to be false, they both have to be true. So when I look at this, you know, I'm saying in this case there is a Wumpus in 1, 1, right? And then there is a Wumpus in one of those three squares, but this doesn't hold, the bidirectional doesn't hold, right? So since there's no stench in S12, that means that there can't be a Wumpus in one of these three squares. It doesn't hold, so we can eliminate this world for being able to tell us conclusively that there's a Wumpus in 1, 3. Okay, so go again. Next possible world. Okay, not 1, 3 is true. Now, according to how does this flesh out? Well, there's a Wumpus in this world accordingly in 2, 2, so we would say true. But again, take a look at S and you know, this column right here. False and true is false. So this is going to hold up. So in this particular model right here, it's holding that rule 6 is holding. There is no conflict, right? It is true because we've got no stench and we've got no Wumpuses in either of these squares. But in these other two models, these other two possible worlds, rule 6 right here, this is not holding because no stench means that, should mean that there is no nearby Wumpus. So since this is false, we can rule out these worlds because it doesn't make any sense. This does not hold, right? Let's see, let's do one more here where we got false and true. I'm skipping you know, a couple of possibilities here, but false, true, false, false. Okay, so now it's true that there is a Wumpus in 1, 3. Okay, so that would make this be false. Okay, now this would make this true because true for 1, 3. Now, false and true, false, right? The rule breaks down. You can't have a situation where you've got no stench but a Wumpus. So this world is invalid. Remember, we were talking about eliminating invalid worlds on the previous slide. Okay, now what would be a possible world where we have a Wumpus, okay, or where we have no Wumpus in 1.3? Okay, well, we could have true here, okay, and we could have the no Wumpus. It's false to say there's a Wumpus in 1.3, so that would make no Wumpus in 1.3 true, right? But we would have to then have, in order for R6 to hold, we'd have to have a Wumpus in either one of these other squares or both. So let's say that there is a Wumpus in 2.2, right? So then that would make this expression, this sentence, true. So now stench in 1.2, right? So this first part, and then the other sentence would be true because we got a Wumpus in 2.2. So then R6 would be satisfied. So this right here would be an example of a model for a world where there is no Wumpus. Everything holds. There is no conflict. You know, the rule 6 holds because it's true that we got a stench, and it's true that we have a Wumpus in a nearby square. Okay, and the configuration is such that the Wumpus is not in 1.3. Okay, so that is one possible world where you could have a Wumpus not in 1.3. But let's take a look at another possible model, right, where you've got the stench, but then you've got the Wumpus in 1.3 and no other squares, right? So in that case, false. It's false to say that there's no Wumpus. Now, does this hold up? Does this expression hold up? Yeah, because 1.3 is true. Now, does R6 hold? Yes, because stench and there's a Wumpus nearby, right? So no Wumpus here in this possible configuration, in this possible world, but here there is a Wumpus, right? So these guys are in conflict. So the only way that you could say for certain that you'd be able to deduce that it would entail that there's no Wumpus as 1.3 is if every single world was like M5, right? Where there was no Wumpus in 1.3 and R6 still held, right? Now, there is an example of a world, just one. All we need is one. But there'll be more if we were to flesh out this entire truth table. The truth table would be huge, but there'd be more than one. And so we can't say, because in certain situations there is a Wumpus. In certain possibilities, certain possible worlds, there is a Wumpus. In others, there's not. Okay, so it's possible that there is a Wumpus in 1.3. So it's inconclusive. So we cannot say, right? The knowledge base does not entail that there's no Wumpus in 1.3. Okay, so the example in the text is just doing what I just did, right? So, you know, when you have, you know, R sub 1, that's representing some rule, some sentence that's being added to your knowledge base. There's no pit in 1.1, right? Because that's the starting square, so R1, no pit. Okay, square is breezy, if and only if there are pits adjacent, right? So if there is a breeze in 1.1, then that must be the case. If that the bidirectional says, well, if I have a breeze in 1.1, then I must have a pit in either 1.2 or 2.1. And if there is a pit in either 1.2 or 2.1, then there must be a breeze in 1.1. Okay, and then if I also have detected a breeze in 2.1, right, because maybe I moved to both those squares during the course of the game, if I detected a breeze in 2.1, then there must be a pit in 1.1 or 2.2 or 3.1. And if there's a pit in 1.1, 2.2, or 3.1, then that implies there's a breeze in 2.1, right? So these are sentences, these are claims that are being added, these are rules that are getting added to my knowledge base, okay? All right, so, you know, I'll let you go through and look at 7.3b on your own, but these are all of, you know, the rules that are present in the 7.3b, figure 7.3b world. Okay, so what we just talked about with those examples was a very, very simple inference procedure. It's almost brute force, right? To where you're like, okay, here's all the variables that are involved in what I'm trying to figure out. Now let me go through and come up with all the different combinations of truth values, right? And each set of assignments of truth values to those variables is going to make up one model, one possible world, right? One possible world. No stench in the square, but no Wumpuses in adjacent squares. Well, that's impossible, right? So, that's not going to, I'm not going to be able to take that into consideration, okay? All right, so we can use that algorithm. So in the example in the text, for that figure, they got a breeze in a couple squares, they got a few pits that they're interested in, trying to figure out if there's a pit there, and that gives us, right, that would give you 2 to the 7th, or 128 possible models, right? Now, as it turns out, for 3 of them, the knowledge base is true, okay? And of those 3, no pit in 1, 2 is true, but a pit in 2, 2 is true in 2/3 of the models, and false in a third of them. So what that means is since P22 being true is not the case in all possible worlds, then you can't possibly know that there is a pit in 2-2 or that there's not a pit in 2-2, because logically it's possible that it could exist in a third of the worlds. You don't have enough information to determine it conclusively. Okay, so here's what the truth table looks like for that scenario, right? There's the 2 squares that you're interested in that you've detected breezes in. Now you want to find out where the pits are adjacent, and then R1 here, and R2, R3, R4, R5, that just corresponds to these rows up here that we set up. And there's 128 possible worlds, so you're not going to go through and be able to fit that on one slide. But here are the different configurations of the truth values being assigned to those variables. Okay, now in only 3 of those worlds is the knowledge base going to be true, as we were just saying, right? So you draw your conclusions based off of these values, right? All right, so here's the truth table and numeration algorithm. So this is just the pseudocode algorithm describing what I just talked about. Create that truth table and then examine the truth table to determine if you can conclude that you can infer conclusively that some proposition that you made is true, or some sentence is true. So as it turns out, remember I was asking, does the knowledge base entail alpha? Now on the whiteboard, what was I asking? Is there no pit in 1-3, right? So the knowledge base does not entail that, right? Because there were possible, if we went through the entire truth table, there are possible worlds where there is a Wumpus in that square, and there are possible worlds where there are no Wumpuses, but the Wumpus is not in that square. So it is not the case that my knowledge base in that example entailed no Wumpus in square 1-3. Okay, so let's see here. So the algorithm itself is sound. It's complete for the reasons that you can read here. It's going to go ahead and implement the definition of entailment, and it's going to work for any knowledge base and an alpha, and always terminates. Okay. All right. So you don't have to look at every single model. There is a finite set of models that you can examine. Okay. Now the time complexity for this really, really bad, right? As you can imagine, when I was drawing up that truth table, you can see that was going to take me a while. Okay. So it's 2 to the end. It's bad. Space complexity, not so bad. Linear growth, because for every variable you have to assign a truth value, and that just grows, one variable at a time. Okay, so that's it for that section. Basically, the big idea is look, you got these propositional symbols in propositional logic, and you've got these connectives, and a model is just a combination of trues and falses being assigned to these propositional symbols. Those propositional symbols represent something in some environment, in some world. Okay, and if you want to make a claim, if you want to see if some sentence is entailed by your knowledge base, then you build a truth table and you assign all the different combinations of true and false to the different variables. Okay, and then you go through and you see if that sentence is true in every possible model. If it is, then you can conclusively say that the knowledge base is going to entail that sentence. All right, so next up, 7.5, we're going to look at propositional theorem proving and another way for being able to answer a question, right? Something that is a little quicker, a little less resource intensive. Okay? All right, so we'll go ahead and we'll see you in that next video. And reminder, if you have any questions, feel free to shoot me an email, stop by my regular online office hours. Doing videos for this class for the first time. First time for you watching them, first time for me recording them. Hard for me to tell how clear my examples are without getting immediate feedback from you. So, if I could have done a better job on anything, if I was unclear on anything, if I was confusing on anything, if I can say anything one more time, just give me a holler and give me the opportunity to address it. I'd really appreciate it.